Good afternoon, everyone. Today, we are very happy to have Jacopo Viti from Infant Florence to tell us about his work on the H bar goes to zero limit of the entanglement entropy. So please take it away, Jacopo.
Thank you. So thank you very much for being here today and for the invitation. So it's a pleasure. And so today I want to discuss this recent work which has been done in collaboration with Giuseppe Mussardo from CISA, and it's about the classical limit, H bar goes to zero limit of entanglement entropy. So it will be published very soon on PRA, and it was also editor suggestion. Okay, so let me start this very fancy slides. So the outline of the talk is the following. So I will start very lightly, let's say, by reviewing a bit entanglement and then also entanglement entropy. Then so basically some definitions and just to be sure that we are all on the same page. And then I will focus on what I think is the main physical point of this work and of my talk, which has to do on what really, at least for me, entanglement is, and this will be explained through a famous experiment which everybody knows, a PRB experiment, but also with analogy that maybe some of you do not know due to the depth of John Bell, which are the socks of Professor Bertelmann of CERN. And this is quite interesting, very simple but kind of useful idea to understand the classical limit of entanglement. And then after this general part, I will focus more on the specific model which I am considering are fermions in 1D. And I show how, give some detail on the analytic derivation of this limit, how it can be defined, and what the result will be. And then finally, I will conclude in section 4. Okay, so let me start this first part. It's about entanglement and entanglement entropy. So probably this is their notion that everybody knows, but okay, just to recap. So let me start by saying what are the main actor of my talk. So I will consider pure state. So here I just want to focus on some pure state psi, which, as you know, it is a state such that its reduced density matrix is a projector, namely trace of rho square is 1. Okay, so basically the physical context will be the way of thinking about this wave function is it will be many body spatially extended state. So it's a state which might contain many particles, 1, 2, 3, etc. And there is a notion of locality, so it will be spatially extended in real space. And to define entanglement as usual, we take our let's say our universe, and then we bipartite into region A and region B. There is, and for me it will be quite important, at least to regularize my calculation. As you see, notion of local Hilbert space, so basically a lattice, which is beyond this real space picture. Okay, and then the Hilbert space will be factorized into two parts, factors. One is HA for the local degrees of freedom of this region, and other one is HB for the local degrees of freedom outside. Okay, dimension of HA is dA, dimension of HB is dB. Everything is fine, and if you choose local bases in region A and region B, and this local basis I call IA and IB, then the many-body state psi is decomposed this way, and this M is a rectangular matrix which has dimension dA times dB, so it's rectangular and complex. Okay, so that's the general, let's say, structure of the state. And so what is entanglement? So let me define it in the usual way. So basically, if we imagine to be an observer that can, or an experimentalist that can access only to region A, so it does not know that exists region B, for instance, or just for him where it's impossible to access it, then if we perform measurement, we observed correlation inside the region A. The information which is needed to reconstruct such correlation in such observables, which is contained in the state psi, I mean in this rectangular matrix M, which I was writing here, it's redundant, okay? In fact, the only thing that you need to completely characterize what you see is the so-called reduced density matrix rho A, which is a trace over degrees of freedom outside A of a projector on the pure state. And in fact, entanglement, so it's important to stress that this holds if I perform local measurement on this region A. And in fact, the notion of entanglement can be understood just by looking at the spectrum of this matrix rho A, which in terms of the matrix M, which I wrote before, is just M dagger. So it's Hermitian and positive definite, or I mean, its eigenvalues are all non-negative. And in fact, if you are able to diagonalize it, the spectrum of rho A will look something like that. So there is a bunch of eigenvalues which are positive, and these are lambda 1, lambda 2 up to lambda d, and then there are a lot of zero eigenvalues. So basically, if d is larger than 1, the number of non-zero eigenvalues of rho A is larger than 1, rho A is no more a projector, and the state that you really observe, if you can access only to region A, is no more pure, but is mixed, okay? And well, if you just use exploit the fact that rho A is Hermitian and can be diagonalized, you will also realize that the spectrum of rho A is equal to the spectrum of rho B. And in fact, these basic properties of the reduced density matrices can be used to at the end prove that the matrix M, which appears here, can be in some sense diagonalized, and this is the so-called Schmidt singular value decomposition, or Schmidt decomposition of M, where you can see that there appears square roots of the eigenvalues of the reduced density matrix on the diagonal. Although this matrix is not really diagonal, but you understand. Okay, so basically the state psi at this point can be written as a linear superposition of states which have the same indices. So you can see that here this linear superposition which contains states on HA and HB only has D elements, okay, where D is the number of non-zero eigenvalues of rho A. Okay, so in fact, a state is said to be entangled if this D is larger than 1, namely if the reduced density matrix, which as I said before, is not a projector. Okay, so that being said, let me move just to last definition, which will be useful in this talk, and this definition of entanglement entropy. So, in fact, we are looking for this. So, as I said, pure state is said to be entangled if D is larger than 1, namely if in this linear superposition more than one term appeared. And it's also important to observe that this decomposition is independent from any unitary transformation that you do on region A and region B. So it's what in the language of quantum information is called these operations. They are called local operation and classical communication. So this writing of the state in terms of the after the singular value decomposition is somehow gauge invariant under local unitary transformation on HA on the Hilbert space HA and HP. So it's quite important. Okay, and then we said that the state is entangled if D is larger than 1, and how we can measure entanglement, and then I will come to main point in the next slide. Well, there are many ways, but the one which is very popular, and the reason is probably has to do with the fact that it can be calculated in many different ways. There are several techniques to assess this object, is the von Neumann entropy of the reduced density matrix. Okay, which is a way of basically quantify how much the density matrix rho A, which is the relevant to the experiment, is mixed. Okay, so well then, as I said, in this way one can define the so-called entanglement entropy. All right, so I already stressed that all this definition, and this is very crucial, they are invariant under local transformation on both the Hilbert spaces. And one property that characterizes, and we see it is quite interesting and important, the entanglement entropy for pure state, and it's clearly follows from the fact that the spectrum of rho A is the same as the spectrum of rho B, is that the entanglement entropy calculated tracing over region A or over its complement is the same. Okay, and this all only for pure states, because clearly if you have, for instance, thermal state, this can never be true. Okay, so it's quite, it's a certain, so all of this, of course, it looks extremely quantum in the sense that we have, exploited all the ingredient of quantum mechanics to arrive to these definitions. Okay. So the naive expectation is that, if we are living as we are in a classical world, somehow, at least in first approximation, and I will be clear on what does it mean, all of this, at least if we look at pure state, all of this definition seems to lose meaning. Okay. All right. Just to conclude, citing a bit of literature, what have been the application of the entanglement entropy in the recent years. It's a huge literature, so I cannot really summarize, and I'm not able to do it, but just let me mention some results which they've been used a lot, and this list is non-comprehensive, and so sorry about that. Well, first of all, it has been and is violated for critical system, and there is a notion of universality. So entanglement entropy at zero temperature displays some universal feature which are used to classify typically critical system and even to measure properties of the conformal field theory which is underlying. One can even construct, since this at the end is an entropy, and we'll see in which sense, one can even construct quantity which are starting from the entanglement entropy, which are decreasing along coarse grainings, transformation, renormalization group transformation, and this has been also a very important observation done by Cassini and Huerta. Of course, there are holographical interpretation of entanglement entropy following Ryu and Takayanagi. And then recently also the dynamics of entanglement, in particular time dependence of the entanglement entropy, has been crucial to understand phenomena like Hawking radiation or thermalization in unitary systems. Okay, so just to say that really it's a huge literature, and all of that is based on entanglement entropy. Okay, so now I want to basically go to the main physical point of my talk, which is, well, how we can really think about entanglement and well, maybe what really this is. Okay, so I'll do the, well, I'll do it with the famous experiment that everybody knows. This is the famous PRB experiment. B is for Bohm, because in fact the spin version of this experiment was proposed by Bohm. Okay, so how it works. So it is textbook example. So and this, it is used to basically illustrate how quantum mechanics might be unusual, let's say. Okay, so the textbook version is the following. So you take, or the popular version, let's say, is the following. So we take a source. This source produces a zero spin particle, which is made of two constituents. So there is a spin up, a spin down, is a spin zero, so that will be in a singlet state. Okay, and then the particle of spin zero disintegrate into two components. One is measured here in one particle is measured by the observer A, and the other particle is measured by the observer B. Okay, and let's say that the first observer A looks for the projection of the spin of particle, let's call it also A, on direction NA, so three-dimensional direction NA, and B does it in a direction NB, which for the moment is equal to NA. Okay, so we assume that NB is equal also to NA. And the textbook version continues like so, saying that, well, imagine that A will measure a spin component which is pointing up in direction NA. Well, then he already knows, or she or he will already knows that even before measuring it, B will find the projection of the spin of the second particle opposite. Okay, so if you assign a real notion to particle B, you really assume that this particle exists independently from A, then you somehow, according to this textbook version, are forced to think that measurement of the spin in direction NA will have determined collapse of the wave function far away, and this far away can be as far as you wish. So basically, even when A and B, they are spatially disconnected. Okay, so this is the let's say APR B experiment, and the fact that the state is entangled is crucial to see this call it non-local correlations between A and B, non-local in this sense. But then, well, you might really think more carefully about this problem, as in fact Bell did it, and think whether this is a real problem or not. Namely, if NA is equal to NB, if the spin is measured along the same direction, is this experiment really telling us something non-trivial about quantum mechanics or not? And the answer that Bell proposes is that, well, in fact, there is nothing that you cannot explain with quantum mechanics in this experiment. You can just think that your source is a coin, for instance, and this coin has just two faces. And for sure, if you toss a coin and you observe that the one face is head, the other face will be tail. So there is essentially nothing quantum in such kind of correlation. You can just think that the source prepare a classical system, and the correlation that you observe are basically trivial classical conditional probabilities. So the example that Bell proposes, which is nowadays famous, is the one of the socks of Professor Bertelsmann, which was a professor in CERN when also Bell worked there. Professor Bertelsmann was a fancy man, and he was famous for dressing apparently socks of different colors. So, for instance, yellow and red. So you could be sure that if you observe a socks that was yellow, the other one should have been of different colors. But of course, this kind of correlation, which is exactly the same, I want to stress, exactly the same as the one that you observe if you measure the spin aligned in the same direction in an APRB experiment, has anything to do with quantum mechanics. Okay, so it's a completely is a phenomena that you can really explain without any notion of quantum mechanics. Okay, in fact, Bell went it further and he proposes famous inequalities to distinguish when really quantum and classical correlation would have been intrinsically different. And to do so, you have to take measurement along different directions. So N1 must be, NA, let's say, must be different from NB in order to avoid this essentially fake phenomena which we can call a Bertelsmann-Stock type of correlation. In fact, as I said, the main point here is that all of this is not encoded at all in the entanglement entropy. Because if we basically observe the result, for instance, of a measurement of spin in region A and spin in region B, they will be perfectly anti-correlated. And more than this, the random sequence of measurement that you observe in region A, well, is nothing that you can infer. Well, let's say it doesn't tell you anything about quantum mechanics. You see, it's just a sequence of numbers, 1/2 minus 1/2 minus 1/2, with probability 1/2 is 1/2, and with probability 1/2 is 1/2. So it's just the Shannon entropy of a bit. And of course, it's the entanglement entropy, log of 2 of the system, okay? So, so then let me basically rephrase this experiment in a different way, in a way that maybe you can perhaps understand where I want to go with this. So suppose now that we take a state S as a source, which is an entangled state built from an harmonic oscillator. Okay, so we have harmonic oscillator state eta, and eta is you know, just eigenstate of the harmonic oscillator with eigenvalue essentially h bar eta plus 1/2. Okay, so the state is prepared this way. We have a state with energy E eta in A and energy, well, corresponding to the quantum number 0 in B, and then the state is symmetrized like that. Okay, so once again, we split the system gets measured into different locations, A and B. In region A, we can access to, let's call it particle A, and in region B, we can access to particle B. I denote this particle, which is really a particle inside an harmonic potential, like a ball. Of course, it's just for the sake of the drawing, with energy E eta. Okay, so, well, then this is really, you know, the type of correlation that you find are essentially the same as the one of the APRB experiment. The entanglement entropy is, of course, again, log of 2. This is a complete quantum calculation. You start with this state, you calculate the trace over the second particle B, and then you do the usual construction of rho A log rho A, and you find, of course, log of 2. Now imagine to consider the limit in which this eta, which is a quantum number, is very large. Okay, so I'm considering the limit in which eta, the quantum number which is associated to the state which I wrote here, is very large. So if you think in terms of wave functions, the wave function of this particle will become semi-classical wave function, and that correspond to the limit h bar goes to 0, as we will see later. But essentially, it really becomes a classical particle by the correspondence principle. Okay, so once again, we observe a particle in region A with a certain energy E eta. We find some correlation, and what is quantum here? Nothing, essentially, because basically we can think that the correlation that we observe from such state in the limit in which eta goes to infinity, they are just like the SOPs of Professor Bertelsmann. If we know that the particle number is conserved, and in this state, the particle number is conserved before and after the measurement. If you observe a particle in region A, of course, there will be no particle in region B. So there's a perfect anticorrelation, but it's trivial. Okay, so, but this simple example already show you that basically we can consider entanglement entropy in the classical limit, where it becomes essentially the entanglement entropy of a bit, because this is the Shannon entropy of what we measure, what we observe, of the random outcomes of the measurement, which have a completely classical meaning. Okay, so this is the main point, and perhaps it should already be stated here. Entanglement entropy, the entanglement entropy is just a number, and it doesn't really tell us much about the correlation that we observe and we measure in the system. This correlation might be classical at the end. Okay, so we must be smart like Bell to devise an experiment to really observe quantum correlation. So entanglement entropy is not just, it's just a number. Okay, in this case, the experiment which one should devise would need to break particle number conservation. Okay, so now let me go to the last, basically let's call it this main part of the talk, where I will try to explain how, well, basically how you can take this limit, how you can think about this limit, the limit h bar goes to 0 of entanglement entropy in a system of fermions essentially opening on a lattice. But the main point, it's already stated with the simple example. Okay, so all right. So let me explain. So let me define the model. So the main question is again the same which I discussed before. Can the entanglement entropy for a pure state and not the entanglement, they are not really, I mean, this is the distinction which I want to make, have a well-defined classical limit? I mean, can this quantity be meaningful for a classical system, the entanglement entropy? Okay, and if so, how you can really calculate this limit? Okay, so the model which I propose is a model of fermions in one dimension. So these are one-dimensional fermions in an external potential. Yeah, I see that there is a question, so please. Christoph?
Entropy for a pure state. So
Yes.
For a pure state, I guess entanglement entropy is 0, right?
Why?
Yes, so
it depends what your bipartition is, why you say 0.
I mean, pure state is defined like entanglement entropy of a pure state is just 0. I mean, there's eigenvalues. I mean, yeah.
I mean, this is the thing that I wrote at the very beginning. No, you
yes. So maybe I got lost at the yeah. Okay.
I mean, at the very beginning, I show you that in fact, any pure state, you can write it like this. Yes, once you have fixed the bipartition of Hilbert space. So if this is so-called Schmidt decomposition. No? If D is 1, then there is just one state, and then it will be 0. But if D is larger than 1, then the reduced density matrix is not a projector, and then it's
okay. Okay. Okay, thank you.
Okay, so perhaps let's say it's surprising that this notion of entanglement entropy for a pure state survive also in this limit, in the limit in which the system become classical. And I'll show you this in this simple example, where essentially this entanglement entropy was really independent on H bar. It's just a number, and it's always a number, but here it's really clear that it does not depend on eta. I mean, on this number here, which is an integer number parameterizing the state. So if I take eta goes to infinity, which is a classical limit in which the wave function of the state becomes really the one, or the WKB wave function, and the particle get basically localized inside the classically allowed region, well, you see this number is stay finite. So, and that's the interpretation that I gave was based on this, on the fact that in fact what we observe is not a real quantum correlation, but the entanglement entropy doesn't know about that. Okay, so fine. So let me then consider the system of fermions in 1D, and so we have so the Hamiltonian is very simple. So these are this C are fermionic operators that anti-commute, and the fermions, they can hop on the lattice due to the first term. They can jump here on sides of the lattice. The lattice spacing is A, which is here. H bar is here, and well, this fermions, they are confined in a external potential Vj. So this parabola shape here is drawn to understand that there is an external potential which confines the fermions. So this Hamiltonian is written in second quantization. Okay, so I need to have an external potential to regularize the wave function, and also a finite lattice, because it's more, at least for me, is more clear than how things go when I will consider the continuum limit. I will consider the continuum limit A goes to 0, where this lattice becomes really the wall line. Okay, so let me start with a simple example. I will calculate so the entanglement entropy of a single particle state. So this is really the example of the harmonic oscillator, which I showed you before, but let's say in a more general setting, view it in a more general setting. So we take a state psi eta, which contains just one particle. So there is just one fermion, okay, moving in this lattice. So here you see that this particle at site J, and the wave function is eta is a parameter which is an integer essentially. I'll show you in 1 second what it is. And so basically, well, this state is entangled because clearly it's completely delocalized. It's a linear superposition of states, and if you calculate, as we will see, its entanglement entropy after defining certain bipartition of the real space, it will be finite. Okay, this is the entanglement entropy. Okay, so just to show why I put this A here, because well, this amplitude psi J, which appears, J is the lattice size, they solve discrete Schrödinger equation. It's very easy to prove. So this is really the discrete version of the Schrödinger equation. With so this particle, you can really think of quantum particle, which energy in an external potential V with energy E eta. Okay, and eta therefore will be a positive integer. Okay. So if I take the continuum limit, the psi j eta, they become the usual Schrödinger wave function. Okay, this will be the usual Schrödinger wave function for a potential v of x, where x is a times j, and a is the lattice spacing. And so eta is basically the quantum number of associated to this to the energy of the quantum particle. Okay, so we have a particle on the lattice, and we want to calculate its reduced density matrix. So the situation is physically like this. We have a potential. This is the potential, external potential. The particle jump on the lattice. We select a region A, which we observe of certain lattice sites. So let's say L is the number of lattice sites that this region is made of. And the region A is inside the classically allowed region. So it's basically is within the region where you could find a classical particle. Okay, so then we observe only local operator within this region, and therefore we calculate the reduced density matrix of the state by tracing over degrees of freedom outside A, which are these B degrees of freedom. And in this way, we determine rho A. Okay, rho A. Okay, so it's an easy exercise to show that rho A, in fact, is just a sum of two orthogonal projectors. One is a projector on a state with zero particle within region A, and another one is a projector of rank 1, in this case, on state with only one particle. And this is quite obvious, no? Because you have one particle moving on the lattice. So either you do not observe any particle inside region A, or you observe one particle. Okay, so that's why the reduced density matrix decomposes like that. So there are just two eigenvalues of rho A. One is basically the coefficient which is in front of this projector. This one will be the first eigenvalue, lambda 0. Essentially the probability to not find any particle here. And then, well, since this is the other projector on the one particle state as rank 1, the eigenvalue is the trace of this matrix, and call it lambda 1. So we can calculate the entanglement entropy of the single particle state. It will be is a pure state. We can calculate its entanglement entropy relative to region A, and it will be minus lambda 1 log lambda 1, where lambda 1 is essentially, as you can see here, the probability to find the quantum particle within A, because here we sum over J belongs to A, and the modulo square. And well, okay, 1 minus lambda 1 will be the probability to find the particle outside. Okay, so, okay, then at this point we can calculate the classical limit of this the entanglement entropy in two steps. First, we take the continuum limit, A goes to 0. Okay, so in this limit, this sum becomes an integral, the function, the amplitude psi j becomes the Schrödinger wave function. And then we take the classical limit in which eta goes to infinity. The quantum number eta is very large. And this limit corresponds, in this case, to the usual h bar goes to 0 limit in the Schrödinger equation. Okay, so basically, the limit in which so first of all, as I said here, continuum limit, this function psi j becomes the Schrödinger wave function. Then h bar goes to 0 limit of the Schrödinger wave function, where the wave function becomes just its WKB approximation. Okay, so here we are. Okay, and then by, again, simple calculation. So let me just say that this is the WKB approximation of this wave function in the continuum limit. We are taking the classical limit, no? So P of eta is the classical momentum of the particle, of the quantum particle with energy E eta, P of eta. And S of eta here, and the exponent of the WKB wave function is just the classical action, okay? And N is the normalization. So this is true inside the classically allowed region, so where also a classical particle can be found. So in this limit, we can really find the value, the classical value for the entanglement entropy. This particle within region A, okay, as I'm drawing here. Okay, so this is a semi-classical WKB wave function, and lambda 1 will be just a classical, the h bar goes to 0 limit of the modulus square of the semi-classical wave function integrated within region A, and this just gives simply the classical probability defined as the fraction of time that the classical particle spends within region A of the particle. Okay, so if we now imagine to be, so what really the limit means for the entanglement entropy is again an example. This finite limit means for the entanglement entropy is again an example of Bell-Bertelsmann-Sock type of correlation. So basically, we are an observer. We can have access only to region A. We don't know anything about quantum mechanics, but we know that we have in a system one particle. We assign a random variable a value 1 if the particle is detected within region A with probability P classical of A, and 0 if the particle is not detected. We register some random outcome of this measurement, something like 1, 0, 1, 0, 0, 0, 1, etc. And the entanglement entropy is nothing but the Shannon entropy of this sequence of numbers, which are, let's say, classical in their origin. Because, I mean, if we are not, we never had classes of quantum mechanics, just explain the observation by saying that we have a particle, classical particle, in an external potential. Okay. So the same can be done with two particles. So basically, we can consider a state with two particles, where now the wave function. So we have particle 1 and particle 2, which are hopping on this lattice. We measure. At the end, we will focus only in the classical allowed region. And the interval A, which we are allowed to observe, is within this classically allowed region. Okay, the wave function will be some antisymmetric, a linear combination of the two particle states. So we particle at site J and J prime, and antisymmetrize over the quantum numbers eta and beta now, because this is a fermion. We can calculate the reduced density matrix again, really by tracing over degrees of freedom in B. So really by standard quantum mechanical operation. The exercise now produce, as you might expect, since we are looking at basically properties of this region, and rho A is enough to completely specify the state within here. So this density matrix now decomposes into three projectors. They are still orthogonal. There is projector on the zero particle state, so no particle within A, with certain eigenvalue lambda 0. There is a projector again of rank 1 on the two particle state, so you observe two particles within region A. Eigenvalue is lambda 2. And then there is another matrix which is more complicated, and it's the projector on the one particle state. So essentially the probability to see only one particle within region A out of the two that we have. And okay, you can see that all these quantities are expressed in terms of this matrix M, which in turns is a combination of the wave functions of the quantum particles. Okay, so there might be a rather nest, in fact. Okay, so the task is to find the eigenvalues of this matrix, lambda 0, lambda 2, and then essentially all the eigenvalues in the one particle sector. Take the continuum limit, A goes to 0, and then take the h bar goes to 0 limit, which amounts to replace this wave function with this WKB approximation and see what we can do. Okay, so this is can be done. I'll tell you briefly how. Can be done because, for instance, if you observe what is the eigenvalue in the two particle sector, basically the probability to find two quantum particles here within this region in an external potential, this probability, which is the eigenvalue lambda 2, is a determinant of wave functions calculated within this region, integrated within this region, the region A, which is of interest. So you see that it's a determinant of two overlaps between wave function. Similar to, if you know about random matrices, what is called emptiness formation probability, basically. Okay, so to calculate, this will be the continuum limit. To calculate the h bar goes to 0 limit, one has to see how to treat this integral when rho, the wave function, they are replaced by the WKB approximation. You can do this by essentially stationary phase analysis. Yeah? The limit h bar goes to 0 here is carried over by doing stationary phase analysis. And this was suggested long ago, also by Wheeler. Of course, it's kind of different setup, but there is an interesting paper by Wheeler where there is a classical phase space interpretation of the WKB overlaps, which I suggested to look at. Okay, so basically, if we do this limit, then we can really get the spectrum of the reduced density matrix for the two particle state in the classical limit. And this is what you expect. So basically the probability to find two particles within region A is the product of the classical probability to find the first particle and the second particle. The probability to not find any particle is the classical value of not finding any classical particle. Here, 1 minus p classical, 1 minus p classical. And the probability to find one particle within region A, one fermion, is basically given by, well, in fact, the spectrum of the reduced density matrix in the one particle sector, it contains just two terms with obvious interpretation. One is the probability to find particle with quantum number mu within region A and not particle with quantum number beta. And the other one is probably to find particle with quantum number beta and not the particle with quantum number mu inside region A. Okay, so if you combine this result, you can calculate what is the classical value of the entanglement entropy, and you really see that it's just the usual Shannon entropy of 2 bits. Okay, so the pure quantum computation reduces analytically, you can really prove this analytically, in the classical limit, h bar goes to 0, to the Shannon entropy of 2 bits. And this is not, these are bits with a certain classical probability to be 0 or 1, essentially. And this, again, is not surprising because the amount of information that we gain from the system by observing it is really the Shannon entropy of 2 bits, which are these classical particles. and I stress that it's important that the number of particles is conserved to really write this formula. Okay, so I'm concluding now just to flash the general case with a bit of effort, which has to do with some combinatorics and properties of determinants and stationary phase analysis and all of that. You can show that the same results, so basically this simple formula for the classical limit, the h bar goes to 0 limit of the entanglement entropy, also holds for a general state with n families. So here is the state. It contains now n particles opening on the lattice, and it's anti-symmetrized over all the quantum numbers. We can calculate the reduced density matrix and the continuum limit, the semi-classical approximation of the wave function, and then the h bar goes to 0 limit by stationary phase. And what you find is that the entanglement entropy of region A, which is again inside the classically allowed region, is just the Shannon entropy of n bits. And these n bits, they have a classical probability to be 0 or 1, and the classical probability to be 1 is the classical probability to observe the particle, the classical particle inside region A. Okay, so this is really the final result. So here is the classical probability of finding the particle within region A, and P of eta is the classical momentum of the particle. Okay, so well, with this, I come to my conclusion. So I try to show you that the entanglement entropy might have classical limit in the sense here defined as the h bar goes to 0 limit of certain wave function, but basically that amounts to take state with very high energy, because it's equivalent to taking quantum states with quantum number which is very high. And this limit is just the Shannon entropy of n bits for the particle which I'm considering, which are fermion. So this is just the Shannon entropy is nothing but the amount of information that it can be extracted from classical measurement outcomes. Yeah, so it's not surprising that this limit is finite, because the system basically, even of course it has no trace of entanglement whatsoever because it's a classical system, but can be observed, and the entanglement entropy at this point is just the entropy of a random sequence of measurement that can be performed on the system that have a perfectly classical meaning. So what I want to also point out is that the entanglement entropy is a measure of entanglement, but perhaps should not be overestimated, because in fact we should be as smart as Bell to really pinpoint difference between classical and quantum correlation. Okay, which in this case amounts to, in my simple setup, amounts to essentially introduce interaction and break particle number conservation, which I cannot do it analytically. Okay, so similar results, they've been obtained by quantum field theory and replica methods, much more complicated than this determinant stationary phase approximation by quantum integrable quantum field theories for free boson. Okay, so free boson on a line with periodic boundary condition. But the quantum field theory interpretation missed, I think, the point of the fact that so there was not, of course, h bar involved in the quantum field theory computation. So I guess it really missed the fact that the value of the finite value of the entanglement entropy for a particle with which in this case they were considering boson with the larger and larger momenta was in fact a classical result that could be derived just by a classical, if you want, statistical mechanics. Okay, so with this I finished, and I really would like to thank you for your attention, and again for the invitation. Thank you very much.
Thank you very much, Jacopo. It's a very nice talk. I think now we can take more questions.
So maybe I can stop. Okay, I can still share my screen.
Yes, probably sharing still better. Yeah, maybe I can start with an easier question that actually confuses me about, like, your eta there. How is it related to the H bar? Like that part.
Yeah.
Somehow.
So basically, if you see here in this is an old story, but essentially you can see from the action here. Okay, so this is WKB wave function. Okay.
Right.
So if you so basically the definition of classical limit is given in terms of ratio between the action and H bar. So S should be much larger than H bar in order for the particle to be classical. Okay, so its action should be much larger than H bar. Okay. So there are two ways to achieve that. One, if you see, is to take P very large. So P is the momentum, no?
Right.
And P very large means that eta is very large because the energy is a function of the quantum number eta. Okay. So sending eta to infinity means basically taking P very large, S very large, and S very large, of course, compared to H bar, which you can take order 1 in this case. Then that's the way in which you can also do stationary phase analysis at the end. Or if you want, that's of course something that it's really your choice. You can think that H bar is going to 0 as a parameter, and that will produce the same stationary phase approximation of the wave functions.
So that means
of integrals involving the wave function, essentially. Because what you really need to do are integrals involving the wave function. And this you do by stationary phase analysis, and essentially you have two ways of doing it. Or you take H bar going to 0, or H bar you take order 1 and you take eta goes to infinity, but they are really on the same footing, these limits.
I see. So that means we are considering only the high energy modes. Okay.
Exactly. So this is a limit of particles which have very high energies at the end. So it's very far from ground state physics. So I'm considering a limit where all these particles, they huge energies. The state is still pure, it's not thermal, but the particles, they have huge energies. So in the microcanonical ensemble, if you want, they have huge energies. But it's true that it's very far from the ground state. Yes. And I can show that in this limit, the entanglement entropy is classical. I mean, it's just the Shannon entropy of a collection of bits.
I see. Actually, a related question is that supposing you have a thermostat, like then, well, it seems to me if we have a thermostat to start with, then it's hard to talk about entanglement entropy on top of that, right?
Yes.
But in that case, is there still some quantity that one can use to talk about the entanglement entropy, or some kind of entanglement patterns between two separated regions?
Yes, you can still construct a measurement of entanglement and using what people call a partial transposition, and basically this goes into the direction of calculating the so-called negativity. And it might be interesting also to understand whether this quantity, which is supposed to measure really quantum correlation, whatever they mean, because at the end, quantum correlation, they have to be defined by some Bell inequality. How this quantity behaves in the limit h bar goes to 0. So it really survive some non-trivial finite value, even classically.
I have a question.
Yes.
Is there any implications of this result on the entropy area law in general? Like what happens, for instance, in general, we say that entanglement entropy may depend on area instead of volume. So when you take this limit to 0, is there any kind of implication regarding this?
This is basically the fact that here the finite result is a Shannon entropy, which is symmetric in the exchange of A and B. And this is somehow can be traced back at the end probably to the area law, because you see, it's not thermal entropy. What I find is not a microcanonical thermal entropy that will be asymmetric in the exchange of A and B. The quantity at the end is symmetric if I exchange P with 1 minus P, which amounts to exchange system A with system B, and reflects the property which I was writing at the beginning, that for a pure state, S of A is equal to S of B. This property here, which at the end is the area law. Well, at least is the one which is used to kind of understand the presence of an area law and not a volume law. So there is still something that survives also classically of this area law, probably, and this is symmetrization between A and B. So that leads really to the Shannon entropy. So the fact that...
Okay, thank you.
Yeah. But it's an interesting point, thank you.
Actually, I still have a question, because so far your analysis goes like went through for the fermion case, right? And I think probably the algebra of the fermion plays an important role there, since you cannot have two fermion of the same modes that occupy the same size, say. But for example, if we consider bosons, then it will be much more complicated, or will the results still hold that the entropy is in the Shannon form?
Yes, I can tell you what the result will be. So it's also interesting. So if you take bosons, so here is the you can do it for this simple example of two particles, let's say. So you can assume that the state now is symmetric. So you can even take eta equal to beta. So two particles, they have same quantum number. The analysis can be repeated, essentially because instead of determinant you get permanence, but since in the classical limit it doesn't change that much, because only diagonal element they matter basically. So at the end, the particle being fermion or boson has not so big impact at the level of the formalism, but it has at the level of the result, because you can show that if there are boson with the same quantum numbers, for instance, the one particle sector, so probably you observe one particle within region A out of two, is not so there are not two degenerate eigenvalues. There is just one eigenvalue with a multiplicity factor 2. And this changes completely the entanglement entropy, because now this formula doesn't hold anymore. And what you get is essentially the entropy of a binomial, which is much less than the entropy of a system of bits, because the entropy of a system of bits scale with the number of bits. So if you have n bits, it's scale like n. But the entropy of a binomial, if you have n essentially coin tossing, if you want, this is a binomial, the entropy scale logarithmically with the number of, as a consequence of indistinguishability, which remains basically. So you cannot distinguish two coins at the same level as you cannot distinguish two bosons.
Right, bosons are indistinguishable, and probably because of this indistinguishability, then the entropy, the entanglement entropy actually is not as large as, say, n fermions.
Exactly, precisely, yes. Precisely because of that.
I see. That's interesting.
Yes, basically for bosons with identical quantum numbers, you get a binomial, and the binomial is the limit of large number of particles. The entropy scales logarithmically with the number of particles, not extensively like here. So the fact that it scales very much less is due to indistinguishability, because you can really distinguish now, and this survives on this limit.
I see. So because for fermions, yeah, indeed, if we have two fermions, actually 4 fermions, if 2 are inside, that create an entanglement, an EPR pair with the 2 outside this region A, then it's counted twice somehow.
Yes.
Because they are distinguishable. Probably for bosons, it's yeah, it's hard to imagine this picture, but I think then, since they are
for boson, you have to think more like a really classical coins, that they are indistinguishable from each other. So if you toss 2 coins, and doesn't matter if the first was head or the second, because you just see the outcomes by modding over permutation of the 2 coins. So,
I see. Yeah, for bosons, we need to make them as a group. Like with group 2 inside and group 2 outside, we don't know or how one is correlated with the other, but these 2 groups are correlated. Then it's good. For fermions, we can think of them as individual particles. I see.
Yes, really like bits, basically.
Right, I see. Yes, that's interesting. That's really nice.
Yeah. Well, let's say boson, as long as the quantum number is the same. Then when the quantum number is different, then they behave essentially like fermions. It doesn't change anything.
Right. If the modes are, the momentum they carry are different, then yeah, it doesn't really matter whether it's boson or fermion. They are distinguishable anyway. But also for Fermi, it's also true, because fermions, basically they are labeled by different momentum or different modes in that sense.
Yes. Yes. So in fact, this quantum field theory calculation was done for boson because it was technically easier, the quantum field theory calculation, which is already complicated because there are a lot of divergences due to this excited state. They have to be regularized in a finite volume. So it's a complicated calculation. it was done for boson, observing already this fact that it was a binomial. But here it's direct. I mean, you can really see it.
Right. Here is direct. Yes.
And for Fermi's, this quantum field theory calculation was not done.
Oh, but then, okay. So basically, in the end, one just needs to integrate over the momentum, or integrate over the modes up to a lower cutoff, right? Because what we want here is higher cutoff, a higher momentum.
Yes. Well, we have to integrate over, yeah, okay, over the modes outside some spatial region that you observe. So, yeah, in terms of the wave function, basically, yes, that's. But this calculation in the quantum field theory setup was in a completely different manner by using replicas and twist fields. So there was not any integration. It was really calculating the form factor of the twist field between the excited state of a bosonic theory and regularize this, and then so it's really a completely different setup.
I see. That's really nice. I think probably that's all for today. I don't know if other people still have some questions. Take the last chance. If not, Jacopo, thank you very much again for this nice talk. And I'm now going to stop the recording.
Yes, thank you.